Generative AI isn't simply remixing existing data, it's synthesizing entirely novel structures from thin air, a profound shift in computational creativity. This isn't mere mimicry, but the manifestation of learned underlying principles. This apparent magic stems from mastering the latent space, a high-dimensional mathematical landscape where every single point represents a unique potential data instance. Be it an image, a functional protein, or a complex system design, it's not about merely storing data, but about inferring and navigating its intrinsic compressed manifold of possibilities. Take diffusion models, for instance. They operate by learning to meticulously reverse a stochastic process of noise corruption, a gradual iterative denoising of a completely random input, until a coherent high-fidelity output emerges. This process is exquisitely guided by subtle learned gradients within that intricate latent space. They don't just copy statistical patterns. They intelligently sculpt new realities into existence pixel by pixel or token by token. Consider its transformative impact in accelerating drug discovery. Here, generative models are not just analyzing existing compounds. They are actively designing novel protein structures, precisely tailored to bind with specific disease targets, or imagine creating privacy-preserving synthetic medical data for rare conditions, enabling crucial research and model training without ever compromising patient confidentiality or requiring sensitive real-world datasets. Older generative adversarial networks, or GANs, frequently grappled with inherent limitations like mode collapse, producing a significantly limited diversity of outputs, and often suffered from highly unstable training dynamics. Diffusion models, in stark contrast, consistently demonstrate superior sample quality coherence and extensive mode coverage, navigating the latent space with robust predictable fidelity, achieving unprecedented realism and fine-grained conditional control. The evolving frontier involves deeper disentanglement within this complex latent space, aiming to isolate specific semantically meaningful attributes such as style, texture, functionality, or expression. This breakthrough allows for far more interpretable and precisely controllable generation, moving decisively beyond broad general prompts towards genuine semantic engineering, where we can actively design and manipulate specific data characteristics with unprecedented granularity. Ultimately, generative AI, through its sophisticated understanding and manipulation of these latent spaces, transforms us from passive observers of existing data into active digital alchemists, empowered to build new realities, design novel solutions, and fundamentally push the boundaries of what is computationally constructible.